Chapter 23 is going to look at atomic physics, and we start our discussion of atomic physics with the end of the 1800s, the beginning of the 1900s, so the beginning of the 20th century, and this is when many physicists and physical chemists were studying electromagnetic radiation and how it interacted with the atoms. One of the things they studied was something called blackbody radiation. Blackbody radiation is simply the electromagnetic radiation that's given off by an object based on its temperature. If we look at a couple of graphs here, we see a chart of temperature and the amount of energy that is produced by the temperature. So if we look at the chart on the left, what we have are a variety of lines. So we have very low temperature here at 200 Kelvin. We go up to 3,000, 3,500, 4,000, and then finally up to 5,000 Kelvin. Area under the curve represents the amount of energy emitted by the object as the temperature increases. And one thing that you notice is more energy is given off as the temperature goes up. In addition, the peak of the curve shifts to the left to shorter wavelengths as the amount of energy given off increases. And we'll see right here in this section, that is the region for visible light. So the shorter the wavelengths, the higher the amount of energy be given off, and visible light is actually in a fairly high region of energy, which is why we see things glow. So again, as the temperature increases, the energy increases and the wavelength shifts to shorter wavelengths in association with this higher energy. What classical physics showed us and what led experimenters to expect is as the wavelength decreased, then energy should go to infinity. What we see on the right-hand graph is experimental data showing that this isn't what happened. So we have similar peaks. Here's our 5,000 Kelvin peak to match a 5,000 peak on the other graph. But what we have here is what the theoretical classical physics equation showed us about the relationship between wavelength and energy. It shows that the energy would go to infinity. The graph, however, shows a different story in that this energy is decreasing to zero as the wavelength gets shorter. It's not continuing on to infinity. That led to a problem. Max Planck studied this, and he developed a theory that he was able to explain the experimental results of the data. And his theory was that energy was transferred in discrete packets, or quantized. And this energy quantization is a function of frequency, and these packets, or these bundles of light, are called photons. What this did is this showed that electromagnetic radiation, in particular light, was actually behaving as a particle. The equation that he developed to show the relationship between energy and frequency is this one. Actually, we're going to tweak it a little bit, and we're going to include information about quantization of this energy. So energy is equal to n times h times f, where n is the quantum number. H is a value called Planck's constant that allows the relationship to exist, and then F is frequency. When we talk about classical physics, we talk about energy in terms of joules, so we use the unit of joules for energy, but that's generally energy on a large scale. When we're talking about atoms, there's a very tiny amount of energy that's involved, and rather than having numbers that have very large negative exponents, we're going to change the energy units, and we're going to change them from joules to electron volts. So that means we need to know the conversion between the two. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. And if you've taken chemistry, or you remember from your first year chem class, 1.6 times 10 to the negative 19 in coulombs is the charge of 1 electron. What we see with Max Planck and a number of other physical chemists, physicists of the time, is we're now looking at a different type of physics. And what we're looking at now is quantum mechanics, as opposed to classical mechanics. Newton gave us classical mechanics. Max Planck, Einstein, Bohr, Heisenberg, and a number of other physicists give us quantum mechanics, which is a way of looking at energy and atoms on a very tiny scale. For the electromagnetic spectrum, as frequency of the wave increases, the wavelength decreases. And according to Planck's law that we just looked at above, or Planck's equation, as the frequency of electromagnetic radiation increases, so does the energy. So what we see is that visible light gives us more energy than microwave or radio waves. So here's a chart of the electromagnetic spectrum. Wavelength is here on the bottom, and so what we're going is from long waves to short waves. Frequency is on the top, so we have low frequency that goes along with long wavelengths, and we have high frequency. In addition, we can see how the energy changes. So we have energy parallels frequency. So we have low energy with low frequency. We have high energy with high frequency, short wavelengths. So with the electromagnetic spectrum, it would probably be a good idea to know the different types of electromagnetic radiation so that we're dealing with radio waves, then microwaves, then infrared, visible, ultraviolet, X-rays, gamma rays. So knowing those 7 different types of electromagnetic radiation in their relative order, probably not necessary except for visible light to have a sense of what the wavelength values or frequency values are, but knowing the order from generally low energy to high energy is what makes the most sense. Let's take a look at a couple of examples using Planck's constant equation or using the conversion from frequency to wavelength to make sure we know how to do the math. Here we're looking at a wavelength of 940 micrometers, power of 10. Micro is 10 to the negative 6, so we have a wavelength of 940 times 10 to the negative 6 meters. And we want to find out the frequency. Well, one thing that we know is that the speed of all electromagnetic radiation in air or in a vacuum is 3.0 times 10 to the 8 meters per second. We're going to assume it's traveling through air unless they tell us otherwise. So the relationship that allows me to go from wavelength to frequency to speed is this one. Again, this should be one that you had from first year chem. I know the speed of electromagnetic radiation because that's a constant that I've memorized. I'm given the wavelength, so now I can find frequency. If I do the math, actually, if I can just plug those numbers into the calculator as they are written, I'll get the correct exponent for my frequency, and I should get 3.2 times 10 to the 11th hertz. What type of electromagnetic waves are these? Well, let's jump back to our previous page and take a look. So 10 to the 11th hertz. Here's 10 to the 12th hertz. Here's 10 to the 11th hertz. Microwaves go up to, it looks like, 10 to the 11th. Infrared goes partway through 10 to the 11th, and then 10 to the 12th is definitely infrared. So we could say high-end microwave or low-end infrared. We're going to say probably infrared, maybe high-end microwaves. Can't really do better than that. That's close enough for us. Now, how much energy in electron volts is carried by one quantum of these waves? So I need to get to energy. I'm going to get to energy first because that's the equation I can use from Mr. Planck. So energy equals h times frequency. So Planck's constant is 6.63 times 10 to the negative 34. The units are joule seconds. Frequency, figure that out as 3.2 times 10 to the 11 hertz. Hertz, remember, is 1 over seconds, so my seconds will cancel. I'm left with joules. Doing the math, I get 2.12 times 10 to the negative 22 joules. Now I need to get to electron volts. Remember that 1 electron volt equals 1.6 times 10 to the negative 19 joules. So I'm going to divide this by 1.6 times 10 to the negative 19 joules per electron volt. And so I end up for energy with 1.32 times 10 to the negative 3 electron volts. That's a lot more manageable number, 0.00132 electron volts.